I have some slides here that I stole from Krista Wilson years ago, and I like going through them because they provide another view on how memory allocators work. So we'll go through the basics of how free lists work, and then we'll go a little bit further and take a look at some ways to optimize an allocator. These, of course, came from a 5600 course, but they're wonderful for 3650. So you'll remember that when we're dealing with memory on a modern system, we're dealing with virtual memory. And virtual memory has some benefits, but it's relevant that every process has its own page table. Page tables happen to get represented as multi-level page tables, as we can see in this picture. But the important thing is that when a user program wants to use memory, and it requests it from the operating system in various ways, whether by using a system call like malloc, or in some cases we can implicitly request memory, like when we grow the stack of the primary thread, the operating system may just automatically allocate additional pages to make space for the stack. So for example, if we call a function and overflow the top stack page or the bottom stack page, the operating system may just go ahead and fault in however many additional pages it needs. Now on Linux, if we want to explicitly request pages, the normal way that we're going to do that is with mmap. It turns out that with the allocator that we actually use, the default GNU malloc allocator, it does occasionally call the sbreak system call, but that's not really relevant to the story. It's simpler to look at it and say that all modern page mappings explicitly requested by a user process happen via mmap. Now, an important thing about requesting memory with any of these things, but especially with mmap, is that the allocations are happening in 4K pages. You can get a whole 4K page, but if you want a smaller piece, the program's going to have to deal with that itself. It's going to have to split up the 4K pages that it's getting from the operating system to use for smaller allocations, like on the heap. So if we're going to allocate less than 4K of memory, we're going to have to do that ourselves. Every process is going to manage its own heap memory. This happens in user space, either in implementations of the malloc and free function. An implementation of a malloc and free function is an allocator in C. So either with malloc and free, or when you're not writing C code, other languages have allocators that work differently. Frequently, in fact, almost all languages use automatic garbage collection. The Java virtual machine is an example of that, and it isn't going to have malloc and free. Instead, Java has new, but that's still doing the same sort of thing, where it has to request big chunks of memory from the operating system with mmap, and then it has to split them up and manage them in user code. Turns out there's a lot of ways to do this. So as I mentioned, we have these two basic strategies. We can have explicit memory management with an API like malloc and free, or we can have some sort of automatic memory management where the programmer never explicitly types free. Really, it's only C, C++, maybe Fortran, maybe D, maybe Rust, I guess Forth are all the languages that I can think of, I guess aside from assembly, where you would do explicit memory management. And even there, in languages like D or Rust, you don't actually frequently type free. There's just some other mechanism where we can deterministically see exactly when something's going to get deallocated. Everybody's using some sort of garbage collection, aside from C. Now, doesn't really matter what language you're using, you're definitely allocating memory dynamically unless you're writing Fortran code and statically allocating arrays, which might happen, but probably not if you're a computer science major. So you're doing this all the time. calling malloc or calling new is one of the most common things that you do, so it's sort of important to understand how it works, because if you have wrong ideas about how the allocator works and what the performance trade-offs are, you can end up writing code, even if you're not implementing a memory manager, just writing random code in a random programming language that's way less efficient than it could be. Now what we want to accomplish is we want to go as fast as possible. We want to make good use of the CPU. We want to maximize parallelism, because modern CPUs are multi-core, and we want to take advantage of the threads that we can have. We also want to make sure that the memory allocator doesn't end up being the bottleneck in a program that otherwise is efficiently using multiple threads. We want to minimize memory overhead. It's no good if we say malloc 100 and it takes 20 megs of RAM to represent that 100 byte object. And similar to minimizing memory overhead, we want to minimize fragmentation. That's most obvious in cases where we allocate a bunch of stuff and then deallocate it. We want to make sure that we can reuse that memory in an efficient way. So these slides go through manual memory management based on free lists and some optimizations to that, and then they also go through garbage collectors. We're not going to cover garbage collectors in today's lecture, but we'll probably get back to this, I'm guessing, next week. So our API in C, per the C standard, is that we have two functions, malloc and free. We're allowed to malloc any size of memory. It can be really small, it can be really big. Free is going to take a pointer, but not a size. And that means that it doesn't map to the system call API. mmap, we take a size, we get back a pointer. munmap, we give it a pointer and a size, and it will unmap those pages. If we want free to be able to call munmap, it's going to have to remember the sizes. And of course, for allocations smaller than a page, it's useful to remember the sizes there as well. And another important thing about programming in C is that we're actually giving the pointers to the programmer. The programmer can do things like cast the pointer to an integer, and that's a well-defined thing to do, and we have to deal with that as the allocator. We can't just assume that pointers are an opaque thing. So we need to keep track of memory usage, track sizes, and get decent performance. One thing that we need to make sure that we deal with appropriately is keeping our heap not too fragmented. So if we have some objects, and then we free some of them, now we have a bunch of stuff on the heap, but it's not all contiguous, it's just wherever it was allocated. And now if we allocate a new thing, and it's bigger than any of the individual spaces, we may not be able to allocate that even though we definitely have enough space on the heap. We want to try to avoid this problem. We can't avoid it in general, especially not with a C allocator, where we're not allowed to move things around. With a garbage collector, we can sometimes move things around, but we do want to minimize this kind of fragmentation. So the way that we're going to solve this problem, and apparently we're running into bugs with PowerPoint online not properly supporting PowerPoint. But our problem here is that we want to be able to track our free memory. We want to do it without having to allocate memory. So as we discussed previously, the trick to do that is that we're going to take advantage of the fact that we're tracking chunks of available memory that aren't being used by the program. We're going to use those chunks of memory as a place to keep the cells of a linked list. The linked list is going to track the pieces of memory that it's stored in. It's a super neat trick. So that means that when we have memory that's free, it's going to be a linked list cell, but we also need to track some information about memory that's allocated. So when we have memory that's allocated, that allocated memory is going to have a header, and in the simplest version of this, the header is just going to be the size of the block. And then we have to figure out what the algorithms are to allocate in free memory. So here's an example of a free list data structure. We have two different pieces. When memory is allocated, it has a header, which in this case consists of just a size. And when memory is free, it's on the free list, and so it's a node in that linked list. In that case, it has a size and a next pointer. Here, the slides are assuming that we're dealing with 32-bit platforms. There's some pieces that assume that. And so this pointer is going to be 4 bytes. This node structure is going to be 8 bytes, 4 plus 4. And similarly down here, our header is going to be 4 bytes. The other thing that these slides assume is that we're going to store our size field is just going to have the amount of space that is allocatable in that block of memory. In the examples that we did in class, we stored the total size of the block, including the size field in the header. I think my way makes more sense, but the slides are doing it the other way, so that's why the numbers don't add up the same way. Now, in order to get started, we need to have a heap. And for this particular example, we're just going to start by allocating our heap as a single page with mmap. That puts us in this situation where we have our heap is 4K. Our head of the free list is pointing to a node. That node has a size listed as 4088, so that's 4096 minus 4 for the size field that we are required to have. So it's 4088 bytes of memory available to satisfy a malloc request. And then the next pointer points to null, indicating end of list. We have one item on our free list, which is the entire heap, which is one page. So if we allocate 100 bytes, then that's going to get rounded up to 104 bytes to have space for the size field. And what we do is we're going to take what was the head of the free list, and we're going to use that to allocate we're going to allocate the space there at the beginning of that block of memory. And we're going to split that block of memory that we found that was 4088 bytes before into two pieces. A piece that is 104 bytes that is allocated, so we return pointer S1 and we set the size field to 100 because that's the size of the user allocated piece of memory. The free list then becomes the rest of the heap. It's still one cell that is the rest of the 4K page that was the heap, but now it's pointing starting after the newly allocated block of memory. We allocate again. Again, we need 104 bytes off of our free list. We have one block of 3984, so we can just go ahead and split that. We return S2, which is our pointer to the newly allocated block of memory, and the free list is now pointing 208 bytes into our heap. Allocate again, another block. Now, to free, what we need to do is, first thing, we're going to declare that our free list is kept in sorted order. That does mean that it's going to take linear time to free, but it ends up being super convenient for coalescing. So when we free S2, that's going to return S2 has a size of 100 plus the header. We have 100 and oh wow, it looks like the sizes on the free list are claiming to be the entire size of the cell structure. I don't know if that's reasonable, but that may be what's going on here. In any case, we're going to go ahead and free S2. That means we have another cell for our free list. We have the cell that S2 is pointing kind of in the middle of, and then we have the head of the free list. To insert onto the free list, we stick it at the beginning. Then we make sure that this is getting inserted in sorted order. In this particular case, it is. S2 was pointing lower in memory than head is right now. So we can go ahead and point head at that new head node on the free list, and we have a perfectly valid free list here. When we free S1, we can do the same sort of thing. We'll point head at the chunk of memory that was pointed to by S1. That points to the next item, which was S2, and that's going to point to the next item, which is the chunk after S3, which is the remainder of the heap. You'll note that one thing that we didn't just do is coalesce. When we free the final block of memory, we now have a free list that's 4 long, and all of our memory is free. An important thing to keep in mind is that pointers that the user had, in this case they're named S1, S2, and S3, their values don't change just because we freed memory. So they're still pointing into the same locations in the same page on our heap. They just don't happen to be valid for use by the user program anymore. So this is why we have to make sure that we don't do any sort of use after free, because things will go terribly wrong. If you write any of those pointers, it's writing immediately where the next pointer is in the linked list cell. Overwriting the next pointer would be bad. Of course, the problem here is that we aren't coalescing in this example, so our free list is divided into 4 regions. That would produce fragmentation. If we tried to allocate 4,000 bytes right now, we couldn't, because there's no single block that's 4,000 bytes big, even though we have 4,000 bytes of contiguous memory available for allocation. So the rule is that free regions should be merged with their neighbors when possible. And if the list wasn't sorted, the slides say this would be n squared. I'm not convinced that's actually true. I think we can do it in linear time. But if the list was completely not sorted and after the fact we tried to coalesce, then yes, n squared is what that would cost. So we can just go ahead and combine the first 2 items because they're next to each other to make one bigger block. We can combine that with the block after it. Then we can combine that with the final block and end up back in the state that we were in when we first allocated this heap, where we have one block of memory, which is the entire heap, or the entire page. Another interesting question is, how do we choose which block of memory we want to use when we have multiple blocks on the free list? So in this case, we have 3 blocks available. We have a block of size 50 at the head of the free list. That's followed by a block of size 16. And then we have a bigger block of size 3596 at the end. We're trying to allocate 8 bytes. And so there's kind of 2 obvious options here. The first most obvious thing is we just take the first thing we can get. So the head of the list is pointing to a block of size 50. The block of size 50 is plenty big to allocate 8 bytes. So if we just put it here, that'll be fine. And that'll look like that. Now, the supposed disadvantage to this strategy is that it looks like it causes worse fragmentation than if we, for example, allocated it into the size 16 block. The research tends to indicate that this question is less interesting than these slides are making it out to be, but we do have this question: do we want to do the first thing, or do we want to find a better place to put it? So the next option is we're going to search through the whole free list and try to find the space that is closest in size to the object that we're trying to allocate. In this case, we have an 8-byte object, so we look through. The 16-byte space is going to be closest in size, and so that means that we're left with a block of size 8, but we get to keep our block of size 50, so we can handle a size 50 allocation, and we get to keep our block of size 3596, so we can handle a 3596 allocation. Unfortunately, the downside to that obviously is that it's going to require big O of n time. The claim is that this other method requires like some faster. First fit here is going to somehow be faster than big O of n time. It's not. This still takes linear time, because it could be that we're trying to allocate 300 and we have to search through the entire list before we find a space that is sufficiently large. So both of these options are asymptotically the same time, although the sort of average case or best case scenario is better for first fit, that we're likely to be able to get an answer without looking at the whole list, whereas with best fit we always have to look at the whole list. So free list review, we started with a singly linked list. We're keeping it in sorted order in order to try to optimize coalescing. That makes free a linear time operation. We're going to coalesce adjacent regions to minimize fragmentation. And we have first fit or best fit, and really it doesn't matter. They're both, as it says here, the worst case in both cases is linear time, and it's claiming that first fit is potentially going to be faster. Another thing that we could do to sort of fancy it up a little bit is to use a circularly linked list in next fit. And I think that may be what the starter code for what the allocator that's provided in the starter code for challenge 2 is trying to do, but I'm not 100% positive. We can go even further and use a doubly linked list. That lets you do some really clever stuff. And then the next option is going to be what the slides call bins, and I like to call buckets, which is just another word for bins. So here's the idea with a circular list. So instead of having we have the head of our list, we traverse the list. Instead of having the last item point to a null, we have the last item point back to the beginning. Now the trick here is that we can go ahead, we can find the end of the list for a traversal by asking if our pointer is equal to the head. That means we got back around to the beginning. But the advantage to, the idea with next fit is that every time we do an operation on this, we can move the head forward one. And that's just going to spread everything out all around the list, and that might reduce fragmentation, and there were some papers that indicated this was an improvement over best fit and first fit. But what we'd really like to do is do better than linear time. The moment both malloc and free are taking linear time, we'd like to reduce that down. Sort of the best we'd expect to be able to do is constant time, so that's what we'd like to do. The idea to solve that is that we're going to replace our singly linked free list with a doubly linked free list. The advantage there is that we can then do operations on this list if we have appointered elements in it without doing any sort of traversal at all. So if you have a pointer into a doubly linked list, you can do both inserts and deletes in constant time at the position that you have the pointer to. But to make it work for this particular example, for coalescing on a free list, we're going to have to complicate up the data structures for allocated memory as well. So we're going to have this Boolean associated with both free memory and allocated memory that lets us look at a block of memory and find out whether it's free without having to reverse the free list to check if it's there. And we're also going to have each allocation have both a header at the beginning and a footer at the end, both of which will have the size. And the reason that we have to do that is because it's going to allow us to find our neighbors. So here's an example of a free block. It's a doubly linked list with a header in blue here and a footer up here in green. Then an allocated block that has the header in the same spot. Header is just the same structure as node without the node pointers. It doesn't have a node in it because this is user allocated memory, but we still have a footer. Now the trick here is that if we want to free I, for example, what we can do is we can look back from the pointer to find the header. The header has a used field and a size field in it. And we can use that size field to calculate how long this user allocated space was that we're freeing. And then we can find our own footer next. And then immediately after our footer, we have the next block on the heap. It's not necessarily the next block on the list. We don't have the list in any particularly sorted order, but we can find the block of memory that's adjacent to the block that we're trying to free, and that comes after it just by doing pointer arithmetic. So we can then check and ask, is this block free? It is. We do that by looking at the free flag in the header, and that means we can just immediately merge these two blocks and have this cell in the list take the place of this cell. So it's like we're going to remove this cell from the list in constant time, and then we're going to insert the combined coalesce cell that is these two into the list again in constant time. Even better, we can go back to the header here, and we can find the cell that's before it in memory. The way we do that is we do pointer arithmetic to look immediately before the size field, and we find the footer of the previous item in memory. And that footer has a size field in it, so we can calculate the location of the previous header or linked list cell. We can check if that's free, and if it's free, we can then again do a coalesce in constant time. A lot of pointer arithmetic. There's a complication here when you get to the beginning and end of the heap. You have to have sort of like fake headers and footers that you then special case in the code. This is relatively complicated code for the benefits, and you need an awful lot of overhead per thing, but you do, with linked lists, manage to get constant time free. I don't know why there's pseudocode here. All right, so we managed to get free to be constant time. We would like to get malloc to be faster. Here it says malloc is a 1. That's not accurate. So what we'd like to try to do is we're going to divide the free list into bins of similar size blocks, and reasonable similar size blocks are going to be powers of 2. And if we have bins of similar size blocks, then we can round the size of requests up to the size of the next bin that we have available, and we can do an allocation out of that bin in constant time. This works great until the bin's empty, and then things get a little bit complicated. So here's an example. We're going to have our instead of having a free list, we have this global variable, which is going to be an array of free lists. In each free list, we're going to have a doubly linked list of blocks of exactly that size. So if we want to allocate a block of size 32, we can come and just pull the first one off the free list. They're all size 32, so they're all identical. And then when we want to free, we can go ahead and free it back onto the list because it potentially has neighbors on the free list. We go check for them. If it doesn't have any alive neighbors, we can just go ahead and push it on at the beginning of the 32-byte block, and those operations all take constant time. The one complication here is what do we do if we try to allocate a block of size 512? There's nothing on the free list for size 512, so we need to find blocks of size 512. The solution that we suggest in the slides is that we're going to split a larger block. So 512, we try to split 1024, there's nothing there. So we try to split 2048. And that raises the question, is it really constant time to go all the way up to the next block that has a thing in it? Or we can see that these things are just about doubling each time. Is it more reasonable to say that our buckets are going to go up some variable amount, and so the runtime of allocation is going to be logarithmic time in this example? And it's not clear how you want to look at it. You could look at it either way. They're both reasonable arguments. Another thing that you can do other than splitting larger blocks, which makes a lot of sense, is you can instead just make these act just as completely separate heaps in each size category. So if we want to allocate a thing of size 512 and the 512 list is empty, we can just go mmap in a whole nother new page for size 512 things, and then just not worry about coalescing with other sizes. 512 is a good example of how that gets a little bit complicated though, because if we want to have size 512 blocks, a page is 4K, so that means we can fit 8 blocks of size 512 into a page. So we could just say we're going to mmap a page, split it into 8 blocks of size 512. Wonderful. Unfortunately, when we add in the size field, the thing that we actually get is a block of size 508. Actual allocations of the power of 2, 512 are pretty common, and so if that's our solution, we end up with this worst case situation for power of 2 sizes. On the other hand, if we say, oh, we're going to round it up and we're going to have the things in the bin of 512 sizes, really they're going to be 516 or 520, so that the size field isn't included in the 512 and we can really allocate a thing of size 512, then we end up only being able to fit 7 blocks of size 520 in a page. If we start to try to allocate pages of size like 1536, then that gets even worse with the sort of fragmentation of only allocating a page at a time. The solution there is that you allocate more than one page. It gets a little bit complicated. But I will say that this binning strategy, or I like to call it buckets, is probably one of the simplest optimizations for getting a easy speed up on an allocator, because it definitely does make a bunch of allocations that are all of the same size basically all take constant time for both malloc and free. And depending on how you design it, you can actually get away with a singly linked list here because you aren't trying to do coalescing. Although for challenge 2, you need to do coalescing, so you need to have some strategy that will work for that. All right, so that's a review of basic free lists and some ideas of how we can start to optimize. Another problem, and potentially a bigger problem, is parallelism. We definitely have parallel programs. The tests for challenge 2 are parallel programs. And we run into this problem where we have a single piece of shared global state. We have multiple threads that are trying to access it. That's definitely a data race. So we're going to need to add a mutex. As soon as we add a mutex, we're going to have contention on that mutex. We also have another problem, which is a little bit less obvious, and that is that when we have multiple CPUs or multiple CPU cores that are accessing objects that happen to be next to each other as far as physical memory addresses go, that's a complication. Specifically, when we have two objects that are within the same cache line on Intel processors, it works with 64-byte cache lines. When we have two objects that are in the same cache line, two CPUs can't really access those two objects at the same time. At any time, the mechanism that the cores are using to try to coordinate communication tends to have a rule that every cache line belongs to one CPU at a time. So if one CPU writes to a cache line, then another CPU writes to a cache line, first the first CPU has to write, then we have to go through a move the cache line over process, and then the second CPU can write. And that's significantly slower than having two CPUs operating on two distinct cache lines. So even without a mutex, if we have things next to each other in memory, we have some contention and slowdown from that. Now, if we have a single free list, then we're likely to get a lot of situations where one thread allocates and we get an object, another thread allocates and we get an object right next to it. And so what we'd like to do is maybe not allocate from the same pool for every thread. And the most straightforward solution to that is just to have more free lists. So we have this concept of arenas, and the idea of an arena when we're talking about memory allocators is just a complete copy of the whole allocator. If we're talking about free lists, then every arena has its own free list and whatever data structures we need. Like if there's a mutex associated with a free list, then an arena is a free list and its associated mutex. If we have a more complicated data structure for our allocator, like the bin structure from before, then an arena is an entire array of bins and whatever mutexes are associated with that. So if we have at least as many arenas as we have threads, and we can convince the threads to use different arenas rather than all trying to bunch up and use the same arena, then that can completely eliminate our contention between threads, because they're simply accessing different objects in completely different locations in memory, and so they don't conflict with each other at all. So per thread arenas or multiple arenas is a good solution. You can see here in the picture, we're showing 3 threads, and it looks like each thread has 2 different arenas that it can access, and that's okay. If we have a lot of threads, we don't actually necessarily need to have more threads than arenas, but we probably do want to have more arenas than we have either physical or logical processor threads. Now there's some optimizations that we can do to speed things up even more, and the optimization that it gives in the slides is potentially a bad idea. So let me explain why it's bad, and then I'm going to go through the optimization, because sometimes it's not bad. So the idea of a slab allocator is that if you have a very specific workload, of how your memory allocations work, then writing your own custom allocator can be faster than using any sort of general purpose allocator. And one thing that you tend to notice about memory allocation is that when you free memory, if you reuse that block of freed memory as quickly as possible, if you try to make memory work sort of like a stack, where you free is push and then malloc is pop, that gets you to reuse memory as quickly as possible. That's going to give you excellent cache behavior. If you free something, it's probably an L1 cache, but you're not going to use it soon. So if you then just allocate that thing again, it's already an L1 cache. The problem comes when you write a custom allocator and it doesn't end up having all the properties that you were kind of relying on in the default allocator. My favorite example of this is OpenSSL. OpenSSL is a commonly used open source library for cryptography, especially cryptography related to network protocols like SSL, or now it's TLS. That's the standard protocol that gets used for encrypting network traffic. HTTPS uses it. So OpenSSL had this major security vulnerability called Heartbleed. And the basic story with Heartbleed is that they decided to write a custom allocator to speed things up. And the way the custom allocator worked was it tried to be as much like a stack as possible, so it would reuse memory as quickly as possible, but it didn't like clean up the memory before reallocating it. So there ended up being a way to do a buffer overflow by sending OpenSSL a particular combination of data, and you could get it to allocate a block of memory and then send you back the contents. It didn't write anything over the block of memory, you just got whatever happened to be in memory when it got freed. And OpenSSL is a cryptography library, so one of the things that OpenSSL really likes to allocate in memory is cryptographic keys. And so this Heartbleed bug would let you randomly get it to send you some memory, which probably would have some cryptographic keys in it, and that just broke everything. An amusing thing when the Heartbleed bug got published is that the developers for OpenBSD, which is a BSD Unix operating system, and their big thing is to be secure by default. The developers of OpenBSD took a look at the code. They didn't figure out what exactly was causing the bug immediately. They did later, but on their first look, they didn't see immediately what was causing the bug, but they saw this custom allocator that the OpenSSL people had put in, and they're like, oh, custom allocators are dumb. We're going to rip that out before we look at anything more. So they got rid of the custom allocator and replaced it with the OpenBSD default allocator. It didn't slow it down significantly. The allocators being slow problem was like one platform 15 years ago. But it did just completely eliminate the security issue with the bug immediately, because the OpenBSD allocator guarantees that it always zeroes memory when it gives it to you. There is no malloc that acts different from calloc. Malloc is just calloc that doesn't have a different, have another like number of items option. But malloc on OpenBSD gives you zeroed memory, and that solved the bug. And so they ended up. I don't know if OpenSSL still has the allocator, but the bug was in the allocator, and that's the sort of problem that you run into when you decide to be unnecessarily clever and sort of drop down a level of abstraction to try to get performance benefits without 100% thinking through the implications of what you're doing. But now that I've gone through that ramble, let's go see the slab allocation plan. It's sometimes a good idea. So this is trying to claim that memory allocators are slow and unreliable. They're not. They're very reliable and super fast. But this plan here on this slide is good for some specific cases. If you're going to do a bunch of allocations of a bunch of objects that are all the same size, you're going to be allocating, freeing a lot. The idea here is that we're going to create this object cache object. When we allocate this cache, its first thing is going to allocate 10 of the object that you want. Then you can call the alloc method on this cache object, and it's going to pop an object off its stack that it had preceded with 10 items. So alloc takes constant time. The first 10 times you call alloc, it takes sort of pop off a stack instantaneous constant time. When you call it the 11th time, it's going to go ahead and allocate up another 10 items, but then the next 10 are going to be a constant time allocation. And so this thing, if you have a malloc function that's even kind of slow, even close to being slow, this is going to immediately speed up malloc for you by a factor of 10. Then free just pushes onto the list, which again is constant time, and because we're using a stack, this is going to have the best possible cache behavior. Again, you don't necessarily want to use this in any situation where security or being able to detect bugs quickly matters, but if you're doing something like a video game, and the thing that you're allocating here is, I don't know, bullets, and every frame you're going to have 10,000 bullets appear on the screen, and then you free them immediately because they hit the target or whatever, then an object cache like this makes a lot of sense and is a good optimization. All right, I'm going to go through a couple memory bugs, and then we'll hold off on the next thing until later. First memory bug. All right, take a look at this slide and see if you can figure out what the bug is. I'll give you a couple of seconds. All right, if you haven't found it yet, pause the video and find it, and then keep going. So the first problem that we have here is that we forgot to free data. So we allocate data right here with this malloc. We never call free. We aren't actually returning data, so whoever's calling this function, they can't free it for us. And so this is a memory leak that's going to cause trouble. Now, if we look real closely, we actually have a second similar problem. We open this file, fp, and we never close it, and we never return it. So we're leaking both memory and a file handle. The file handle leaks probably worse, but we're talking about memory bugs, so we'll worry about the memory bug for now. Here's a couple other problems that we can have. We can allocate some memory, we can then free it, and then we can look at what was there. And this may or may not cause the program to crash, this may or may not cause terrible trouble, but it's not legal. We're not allowed to do this, and depending on why we look at the data, we're getting completely random data. Here we're just printing it, so we're just going to print some junk, but if we relied on it having some specific value, it's not necessarily going to have that. In fact, free probably replaced the beginning of the object with a next pointer or something. Even worse, we have double free. And you may have run into the situation already where GNU malloc, when you free something twice, tries to make the program immediately crash with a double free error. It works really hard at detecting them. And the reason for that is pretty clear if you think about what happens when you free something twice. Think about that for a second. The problem is that in the best case, your object ends up on the free list twice, which means that then at some point in the future, you're going to allocate one of those things, and then at some point further in the future, you will allocate both of them to two different objects. So then some arbitrary object in your program is going to write to a pointer, and that's going to result in overwriting some other arbitrary object in your program. And it's from a bug in some completely different part of the program. It doesn't even have to be in the same library, because this is corrupting the heap, which means that the shared malloc function for the whole program is going to, at some point, produce bad answers which corrupt arbitrary data and break everything and be impossible to debug. So yeah, double free is bad. All right, so next up on these slides is garbage collectors. We'll get back to this for a lecture probably next week.